Operating systems. We use them every day, but how do they work? This is a very complex topic, so I will only briefly cover a few aspects of it. My name is Philipp Schauer. I am a student at the HTL Ungargasse. Let us begin with establishing what an operating system even does. An operating system is a program or set of programs that provides access to the basic computer resources provided by the present hardware. Most modern operating systems create an environment in which an application can run safely and without interference from other applications. In addition, many operating systems offer an abstract machine-independent interface to hardware resources that is portable across different platforms to applications. Now that that's out of the way, it's time to ask some research questions to answer in this video. How does the kernel get loaded into memory and then get executed? Booting an operating system commonly starts with some firmware, like the EFI or the BIOS loading a bootloader from a storage device into memory and running it. But what's a bootloader? It's a program written to load the more complex kernel into memory, set up a suitable environment for the kernel, and finally transfer control to it. There are different kinds of bootloaders, also depending on the system that it's supposed to run on. Those can for example be platform-specific bootloaders, like an x86 legacy BIOS bootloader, which resides in the boot sector of a storage device. The BIOS transfers the 512-byte long boot sector from each device into physical memory, and if a certain flag is present, the BIOS passes control to the bootloader. The bootloader must now load the kernel into memory from a file on the storage device, set up a suitable environment for the kernel, and pass control to it. Fitting all this into a short boot sector would be near impossible. To solve that, a second stage bootloader is placed in a flat binary file which is loaded into memory by a boot sector's code. The second stage bootloader would not be as limited in size and thus could load the kernel into memory, set up a suitable environment, and finally hand over control to the kernel. Luckily, these kinds of bootloaders are being increasingly replaced by ones that are portable across a number of different platforms. One popular example would be the EFI bootloader. EFI boots from a specific PE executable file in a file system and even sets up a suitable environment. It also provides relevant information for the OS and several boot services, like a file system driver. All of this answers the previously asked research question. How does the kernel get loaded into memory and then get executed? The firmware first loads and runs the bootloader then loads the kernel into memory, sets up a suitable environment and transfers control to the kernel. The next question is, how can an OS ensure that processes don't get in each other's way by writing to the other's allocated memory area? To answer this, we first have to take a look at the CPU privileges. A modern general-purpose OS often needs to regulate access to certain CPU instructions, memory and hardware resources to prevent a user process from executing instructions that could subvert the protection mechanism, access other processes' memory, or access hardware it doesn't have permissions for. This is managed partly by the memory management unit and partly by using privilege levels. An example of a widely used processor architecture that has privilege levels would be x86. In x86, these privilege levels are called rings, as they can be pictured as circular rings with the least privileged one on the outside and the most privileged one on the inside. They range from ring 0 to ring 3. Ring 3 has the least resource access and the most protection and is typically used by user programs. Ring 2 and 1 don't allow the usage of privileged instructions, but other aspects such as I/O communication to hardware can be configured with different access levels. Rings 1 and 2 are rarely used and are not present at all on 64-bit processors. Ring 0 is used by the OS kernel and has the most access to resources and the least protection. Or has it? In 2005, CPU manufacturers started implementing the so-called hypervisor into the x86 processors, which allows for hardware-assisted virtualization. The hypervisor is also informally known as ring -1, as it's more privileged than ring 0. But there is in fact an even more privileged mode called System Management Mode, otherwise known as ring -2. It's meant to be used by the firmware to automatically perform low-level system management operations in the background while an OS is running, like changing fan speeds, checking CPU temperature, or adjusting CPU speed. A vulnerability that has remained hidden for 14 years, discovered in 2015, allowed the execution of arbitrary code in system management mode. This allowed, for example, destroying hardware by disabling firmware controls and intentionally overheating it, or installing a rootkit into the firmware invisible to the OS and antivirus software. Diving even deeper reveals the Intel Management Engine, aka Ring-3. This is actually not part of the processor itself, rather a microcontroller on the soft bridge running an operating system called Minix. It has full access to the entire system and even runs when the computer is turned off. Additionally, it's almost fully undocumented. One of its features is the active management technology, which runs a web server that allows complete control of a system via a password-protected web interface. The password can be bypassed due to a vulnerability discovered in 2017. Using a 19-line Python script, computers can be hacked even if they're turned off, as long as they have power and an Ethernet connection. It was speculated that this was a backdoor explicitly implemented by Intel. Researchers later discovered a hidden bit inside the management engine's firmware code that when set to 1 would disable the management engine. Intel later confirmed that the function was implemented on behalf of the NSA, so they could use Intel's system without the risk of leaking highly confidential information. But enough about backdoors. Another processor architecture that has privilege levels is ARM. The ARM privilege levels are called processor modes. User mode is usually used to run user programs. Memory access is restricted and reading directly from hardware devices is impossible. All of the other modes are privileged and each of them serves a different role. The next topic is about interrupts. An interrupt is a signal which tells the CPU to stop what it's doing, process a short interrupt service routine, and then return to its prior task. These interrupt service routines can be configured through entries in a table called interrupt descriptor table in x86 or interrupt vector table on ARM. An interrupt can be triggered by both software and hardware. This can be used, for example, to immediately output a character to the screen when a key is pressed on the keyboard. As mentioned earlier, memory management is a system that restricts a process to accessing only its own memory. The memory management unit is a piece of hardware on the processor that translates a so-called virtual address into a physical address. While physical memory refers to the actual bytes on the hardware of the primary memory, virtual memory is a system that on access translates a memory address to a physical address. The OS can map virtual addresses to physical addresses. A common technology used for this is called paging, which splits up physical memory into equally sized pages. It's also possible for a virtual address to not point to any physical address, which causes an exception on access. This can be useful when swapping out memory to disk. In this process, parts of the physical memory that contain data that is not currently being used are stored on a storage device, such as a hard disk, to free up primary memory. When a program needs to access this memory again, an exception is triggered and an interrupt service routine of the operating system copies the data from disk back to physical memory. As mentioned earlier, user programs run in an unprivileged mode, which means that they by themselves are pretty much powerless. Therefore, a user program calls kernel services with so-called system calls to interact with the system. System calls are often invoked via a software interrupt. Since the kernel runs with high privileges, it's important that it checks the arguments it receives by a user program to protect against malicious or buggy programs. With this info, we can now answer the second research question. How can an OS ensure that processors don't get in each other's way by writing to the other's allocated memory area? Modern processors have a memory management unit which allows the system to restrict memory access for different processes to only their own allocated memory areas. The commonly used scheme for this is called paging and involves mapping virtual addresses to physical addresses. Each process is given its own virtual address space through which it can only access its own memory. Multitasking systems automatically divide the available processor time between multiple tasks thanks to the scheduler, the part of the OS that makes it possible to run processes seemingly simultaneously by switching between active tasks very quickly. The scheduler decides which process to switch to next, and it has a big impact on the responsiveness of the system. Moreover, it must preempt each process when its allotted time window is used up. To achieve this, the kernel uses a hardware timer that periodically triggers an interrupt, which in turn calls the scheduler. This is called preemptive multitasking. In a preemptive multitasking system, task switches are not only caused by the task voluntarily giving up its CPU time, but also when the scheduler decides that the task has used up its allotted time or a higher priority task needs to run. And with this we get to probably the most interesting part of this video. Task scheduling algorithms. They determine the amount of CPU time allocated to different tasks. They They should distribute resources fairly among all tasks and must scale well. Let's compare two algorithms with each other, round robin and multi-level feedback queue. Round robin is a very simple and easy to implement task scheduling algorithm. When using this algorithm, the scheduler uses a looping queue to switch through every task in a fixed order. Each task has the same chance of being selected and has an equally short time unit of execution. Multi-level feedback queue, on the other hand, prioritizes tasks with low CPU usage and divides tasks into differently prioritized queues based on their CPU demand. If a task consumes too much CPU time, it's moved to a lower priority queue. Similarly, a task that waits too long in a lower priority queue can be moved to a higher priority queue, which results in long processes being automatically moved to lower priority queues while interactive processes remain in higher priority queues. To see which of these algorithms performs better, we can run a test. With a program that spawns 50 threads, each of which is either CPU heavy or uses very little processor time by preempting itself. By recording 510 test runs per algorithm, 10 test runs with 0 processor heavy threads and 50 self-preempting threads, 10 test runs with 1 processor heavy thread and 49 self-preempting threads, and so on. Before looking at the results, I should explain a few terms. Running time is the time the task spent executing on the CPU. Waiting time is the time a task spent in the ready state waiting for a CPU. And turnaround time is the time between submission to completion of a task. The results show very similar running times per second for both algorithms. It looks like round robin performs slightly worse, but this is because there is actually another process that is responsible for idling the CPU, and round robin doesn't favor one task over another. More interesting is the waiting time of the preemptive tasks. While with round robin the waiting time increases with the number of processor-intensive tasks, it hardly changes at all with multi-level feedback queue and results in good response times. The turnaround time of preemptive tasks follows their waiting time very closely. As for the overhead of the scheduler itself, multi-level feedback queue outperformed round robin. So let's answer the third research question. Which process scheduling algorithm performs best? Of those tested, multi-level feedback queue was the clear winner. Although it is more complex to implement than some other algorithms, interactive tasks achieve very good response times, and CPU-heavy tasks have a chance to recover their position in a higher priority queue if they behave well. Takeaways: a bootloader is a program to load the kernel. Each process is given its own virtual address space through which it can only access its own memory. As for task scheduling algorithms, multi-level feedback queue generally has better response times for interactive processes than round robin. Thanks for watching.